Hi, so in this class we're going to look at parametric facades. Assignment 3 will be focusing on creating a lookout tower in the sort of cargo container holding area north of Dusty Greenwell Park. So in the classes, or the days class files, so 200309 parametric facades, I've thrown a few examples in here. The first one we're going to look at is this this apical reforms design workshop in Ahmedabad in India. Sorry for the pronunciation, but we are going to start with doing something sort of like this. Now we're going to do this in two ways. The first way is we're going to use attractor points, so it might be a little bit of a review. The second way we're going to do it is with a image sampling. And then after that, we're just going to look at a few different sorts of things we can do with those methods of creating a parametric facade. Following that, we'll start to look at solar angles and deriving a facade from solar data to come up with something more like the Emerson College facade in LA by Morphosis Architects. So starting to work with environmental data to sort of derive interesting facades. Furthermore, we'll look at using things like view corridors or points of interest that you want people to look at in your lookout tower to derive a facade that way. So that's what we'll be covering this week. A few examples in here of the sort of forms, the languages maybe that we'll go through. So with that being said, we'll start with something like this. In Rhino, you can open a new window. Now, all you want to do is you just want to make sure that you're working in the same units as your site model. So that might be in meters. Since we're not going to be referencing the City of Vancouver data anymore, it might actually be worth switching to millimeters. Usually that's sort of the metric architectural scale, so I'm going to work in millimeters. Again, you can work in meters if it makes more sense to you. And you can work in your site model, the assignment 1 site model, but I would encourage you to kind of work on this lookout tower, at least the first few studies, in isolation, and then always integrate it back into your site model later, similar to how we've done the bridge. So again, our reference image is this facade right here, so we're going to create these undulating pickets almost. And even though this is done on multiple, walls, we're going to start out with just working on one wall. So what I'm going to do is I am going to draw a curved wall. I guess it'll be more than one wall, but I'm just going to draw something like this. Your shape can be different. Again, at this point, we're not so much focusing on the form of our lookout tower, but rather the methodologies that will inform our lookout tower. I'm going to be presenting these techniques in a way that will allow you to sort of pick and choose what you want to do. So if this formal language isn't your cup of tea, we'll be covering other things. So I'm just creating a curve. I don't know why I keep adjusting that. And what I'm going to do from this, make sure it's in 2 dimensions, is this is kind of curve is going to form the wall that I'm going to use for this offset. So what I'm going to do is I'm just going to select it, and then I'm going to hold Alt in Rhino and drag it up with the gumball, and I'm going to create 2 of these. And I'm just going to reference these in Grasshopper to create a basic surface that we're going to work from. You know what? I am going to do something that's more, I guess, in one plane. Like that. So again, just select your curve, bring it up like this. In Grasshopper, so I have my Grasshopper window here. To reference these curves, we're going to go to Params, Geometry, Curve. We're going to put that component down on the canvas. We're going to right-click this and go to Set Multiple Curves. And then we're going to select these curves from the bottom up. So in the future, you might have more than 2 curves, so that's why the order is important. We'll right-click the curve parameter, and we'll just call it input curves. Maybe you want to put profile curves. And then what we're going to do is we're going to go to surface, freeform, and then loft. So loft, it's similar to loft in Rhino. Create a lofted surface through section curves. We're going to take our input curves parameter and plug into the C input, so the curves input, as well as there's some loft options here. Feel free to go through them. For this tutorial, I'm just going to leave it as the default settings. Now what we're going to do to create this is we are going to start by creating points on this surface. And we're going to create these undulations first by doing attractor points. So essentially, the closer a point on the surface is to a point that we sort of draw in Rhino, the more, I guess, undulating it will be, the more it'll pop out. So maybe what I'll do right now is I'll create those attractor points. So in Rhino, I'll create 2 of them. I'll just click the single point button there. I'll click it again. I'll make 2 points like so. Maybe 3. Doesn't matter. I'll select those points. I'll go to params, geometry, point. I'll put this point component down on the canvas. I'll right click it. I'll name it attractor points. And I will set multiple points. So now these points are referenced. So what I'm going to do now is I'm going to create a bunch of points on this surface that will be referencing in relation to these points here. So we're going to figure out the distance to these attractor points. So to do that, I'm going to go to Surface, Utilities, Divide Surface. So generate a grid of UV points on a surface. I'll take my loft, I'll plug into S for a surface to divide. And now you can see I've generated some points here. Now, we probably want to change the number of U and V segments. So I'm going to create 2 sliders. So I'm going to double click on my canvas, and then I will create a slider by saying we want a minimum of, let's say, 4 divisions. So I typed 4, and then I'll type less than, I'll say a max 50. I'll hit enter, giving me a slider. I'll go Control C, Control V to copy it. I'll plug the first one into U. I'll plug the second slider into V. So if I move the U count like so, yours might be different, but for me, when I move the U slider up and down, it's essentially giving me the amount of points in the vertical direction. So I'll right click on this slider and I'll call it points in vertical. Excuse me. The V count here, if I move it back and forth, we can call this essentially points in horizontal. So I'll right click this slider and go points in horizontal. So points in vertical, points in horizontal. Now, when we look at the output of these points, you can see that they are in a certain data structure. So to get a better idea of this, you can see there's a bunch of leading zeros. So leading zeros, if we've sort of mentioned in class, if we think of, why don't we go to params, utilities, param viewer, plug the points into param viewer. So you can see that there's 11 branches in this data set. The leading zeros here are empty branches, and then there is one sort of meaningful branch. So the way we can think about this is we have one box, which is this first 0. So you can see that all of these branches share the same 0. Then we have a second box, excuse my scribble, that also has the path 0. So 0 is shared by all of these. But then we get into unique boxes when we get to the third digit here. So we can think of this as having 1, 2, 3, 4, 5, and so on and so forth. I won't draw out all these boxes, but these are sort of the containers for our data. So corresponding to 0, 1, 2, 3, 4, and so on. So that's what this data structure means. If we wanted to get rid of any of these superfluous branches, so any of these boxes that are shared by all data, we can right-click the P output and click Simplify. So now what this means is rather than having this box within a box, we literally just have a box 0, a box 1, a box 2, and so on, so on forth until we get our box 10. Now, the reason why this is important is because within each of these boxes, we have 27 points, right? Now, these 27 points are going to correspond to either our points in the vertical or the points in the horizontal. In this case, we can see that we've divided our surface into 26 horizontal units. So if I increase this, you can see that the points in each branch increase. It's always one more than our points in horizontal slider. So we know that these branches relate to the horizontal grouping of points. If we increase the vertical count, you can see that the number of branches increase, but the number of items in each branch stays the same. So what that means is that the vertical count corresponds to the branches themselves, so the containers, the boxes themselves. So of course, if we go to Curve, Spline, Interpolate, and plug our points into the V input, you will see that we will draw horizontal lines because these points are grouped as horizontal groupings. Now, if we look at our precedent image here, these pickets are vertical. So how are we going to take these points and translate them from horizontal lines to vertical lines? So essentially what we need to do is we need to swap the data structure so that these points are grouped vertically. And to do that, I'm just going to delete these scribbles. We can use a component called Flip Matrix. So we can go to Sets, Tree, Flip Matrix, put that on the canvas, put our points into Flip Matrix, and then let's go to Params, Utilities, Param Viewer, plug in our Flip Matrix data, and now what you can see is that instead of having 36 items in each of our 16 branches, we have 16 items in each of our 36 branches. So if we plug our Flip Matrix component into our vertices input of our Interpolate Curve component there, you can see that now we get vertical lines. So this is kind of what you want to think about when you're dealing with data management, and this is why data management, graph, plan, simplify, etc., is actually important. It does represent the way that data is actually considered in Grasshopper. So we know now that our points are being considered in vertical groupings. We have our interpolated curve in the back there, and that's great. And we're just going to leave this for now. So what I want you to do is we can delete these param viewers. We've sort of used them. And what we can do is we can group all of our subdivide surface components, our flip matrix component, our loft component. So these right here, we can group these, and we can just call this group subdividing surface. And our interpolated curve, we can just sort of put this to the side for now. We will use this later, but we won't worry about it. Maybe I'll actually just delete it just delete it. Know that these points are now organized vertically. So we have our points in our subdivided surface, and we have our attractor points. The next thing we want to do is actually figure out the distance between these attractor points and these points in the vertical groups. So to do that, what we're going to do is we're going to go to vector, point, and then we're going to go to closest point. So vector, point, closest point. So find closest point in a point collection. The P input is point to search from. So what we'll do is we'll take our flip matrix points, we'll plug into the P input. Now, if we look at this, again, if we hover over our P input, we can see that branch 0 has 16 points. Branch 1 has 1 point, or 16 points, sorry. So what that means is that we're considering these vertical columns of points as groups. What we actually want to do is measure the distance from each and every one of these points to these attractor points. So to do so, what we're going to do is we're going to right click our P input and go graphed. And what graph does is now you can see that there's a branch 0, 0 has 1 point in it. 0, 1, it has 1 point in it. 0, 2 has 1 point in it. So what this means is that in the 0, 0 branch path, the first 0 refers to the column. So you can see if we hover over the P input again, the first number goes from 0 to 35, representing the columns from 0 to 35. And the second number in that path is the point in the list. So in other words, the first number represents a column 0. The second number represents the point 0. So if we hover over P input, 0, 0 is right there. Hover over P input, 0, 1 is that one right there. Hover over P input, you can see the last value here has an address of 3515. If you were to count 0, you would end up at 35 right here. And then the second number, if you were to count from 0, you'd end up at 15 down here. So that's what that means, and that's why we graphed right here. The attractor points, we can plug into the C input, cloud of points to search. So now what this gives us is the point that's closest. So it's going to be one of these 3 points, but then it also gives us the distance. So the distance to the closest point. So it'll only give us, let's say, this point right here. It's going to measure its relation to all 3 of these attractor points, and it's only going to return the distance to the closest one. So that one right there. So if we want to visualize this, we essentially need to sort of map out the distance between a single point and the attractor points and where that sort of lies in relation to the entire set of points. So what I mean is we're going to figure out what's the closest value, what's the furthest value. So to do that, we're going to go to Maths, Domain, Bounds, and we're going to take our distance output and we're going to plug into bounds. Now if we look at the input of bounds, we're putting in all these single values. They're all in their own list. 0, 0 has 1 value. 0, 1 has 1 value. So the output is we're getting 576 bounds. We want to look at all these distances at once. So we want to figure out what the closest distance is and what the furthest distance is. So to do that, to put all these distances into one list, we're going to right click the N input, so numbers to include in bounds, and we're going to click on flatten. And now you can see we only get one output because all the values are being considered at once. They're in one list. So the values go from 96 to 408, meaning that the closest one of these points is to an attractor point is 96. If I were to move it closer, we would see now it goes from 19 to 408. So what we can do now is we can essentially map these points in relationship to these bounds. If we want to visualize it, we can do something here. We can go to params, input, gradient. And we can just use this to kind of visualize the relationship of these points to these attractor points. What we want to do, so the gradient, it has a few inputs. It has the lower limit of its range. It has the higher limit. And then it has the value. So L0 and L1, it's going to correspond to the numeric domain we have here. But this numeric domain needs to be broken up into its constituent parts. So let's go to maths, domain, deconstruct domain. We'll take the bounds output, plug it into the deconstruct domain component. The start will go into L0 in our gradient. The end will go into L1 in our gradient. And the values will be the distances right here. So this is just converting these values to a whole bunch of colors. What we can do now is we can go to display, we can go to preview, custom preview, and what we want to preview are our points here. So we'll take our surface divide points output, we'll plug into the geometry input. In this case, we want to sort of match the data, and the easiest way to do that is just to flatten both of these inputs. So essentially it's going to sort of match list to list. So we're going to make sure your surface divide points are going into G, and then your gradient output's going into M. And essentially, when we turn off our other components, so let's turn the preview off here, you're seeing the relationship that we've made between all these points. Of course, the reason why this isn't looking correct is because instead of putting your surface divide points into the geometry input, you need to take your flip. So remember, we flipped the matrix. Let's plug that into the geometry input, and that looks more sensible. So sorry, the flip matrix output goes into the geometry input. So now what you're seeing is you're getting this kind of heat map of the relationship between these points. So as we move these points in and out, you can see that it's finding the closest point, it's figuring out the range of distances, and then it's sort of coloring these points in relationship to these attractor points. So that's kind of interesting, but what we're ultimately after is something that looks like this, right? So we're going to take this gradient, the domain start and end in the preview. We're going to move it up here. So disregard this other stuff I have here. We are going to take the domain start and end, the gradient in the preview. We're going to group it. And I will just call this attractor point color preview. And this is just something we did to sort of get a sense of how this is working. I'll go preview off. And then from here, maybe I'll just preview on my flipped points. And that is all I'm going to preview on at this point. So we have our bounds coming out of our closest point. What we're going to do is we're going to remap these distances, and we're going to use those remap values to move these points. So what I mean by that is we are going to go to maths, domain, and then we're going to go to remap numbers. And maybe I will leave the preview on for my custom preview here. It'll be a little bit easier to explain. So remap numbers. So remap numbers into a new numeric domain. Essentially what that means is if we look at our values here coming out of our bounds, so we, in my case, have 60 to 325, we can think of this as a list of numbers going from 60 to 325. The halfway point, let's consider this halfway point is about 60 plus 325. 380, 130. I think it's around 190 or something. Let's say its halfway point's 190. Bit late, so mental math is not the best right now. If we were going to remap this to, let's say, 0 to 1, this 190, this midpoint, would be remapped to 0.5. So that's what remapping does. It takes the position in this original range, so 60 to 325, and it remaps it proportionally to a new domain. So in this case, 0 to 1. So the values to remap will be our distances here. The source domain will be our bounds, so 60 to 325 in my case. And the target domain is going to be our surface offset, so that's going to create undulations like this. So what we'll do is we'll create this with some sliders. We'll go maths, domain, construct domain. So right now, by default, it's 0 to 1, so we're remapping to 0 to 1. But what we want to do is we'll use two sliders. We'll double click on our canvas. And I'm going to go negative 500, less than 500. Maybe I'll even do negative 5,000, less than 5,000. Hit enter. And I will copy this slider and plug it into the domains. Now I'm going to start with, let's say, 0 to 1,000. Now the reason why I did negative 5,000 to 5,000 is because this will control which side we're offsetting. So maybe I want offset on this side, maybe I want offset on this side. Going into the negative range of numbers, it's going to give me that control. But, you know, to start out with, I'll set my domain to be 0 to 1,000. So now we get a bunch of values here. Now, what we can see here is that, like I said, if we look at our flip data output, so that's these points here, they are organized in vertical columns, right? So each vertical column is its own list. If we look at our remap values, each value is in its own list. So, for example, what I'm going to do, just for the sake of example, I'm going to change the amount of points in vertical to 4 and the amounts of point in vertical to 4, just to show you what's happening. So what's happening right now is we have in our flip point, or our flip matrix component, we have 1, 2, 3, 4 branches. So 0, 1, 2, 3. In each of them, there's 4 points. So I'll just draw 1 point in each. But each of this is times 4. Because we want to look at these points in isolation when we are finding the closest point, the output of our remap values is going to have 4 boxes, so corresponding to our 4 boxes above. So 0, 1, 2, 3. So 0, 1, 2, 3. But since we grafted at this point here, when we put our flip matrix into our closest point, we grafted there. What's happening is these 4 points are not in the large boxes. We made 4 smaller boxes in each one of these large boxes. And in each of these, there is 1 point like so. Now, what we can do to get these back into their boxes is we can use a component called trim tree. So, and that will essentially get rid of the smaller boxes and move 1 level up our tree structure. So to do that, we'll go to Sets, Tree, Trim Tree. So reduce the complexity of a tree by merging the outermost branches. The remap numbers will be we'll take the output of remap numbers, plug into the T input, that's data tree to flatten input of trim tree. And then now what you should see is we have, in this case, 0 branches, so 0 to 4 corresponding to these vertical columns. And then you can see 5 items in each branch, so 0, 1, 2, 3, 4, 5. So, but I will now increase my points again to get a little bit higher density, like so. The important thing is our data structure coming out of the trim tree is the same as our data structure coming out of the flip matrix component there. So now that we have these values, what we can do is we can move these flip matrix points based on these values. So these values are going to correspond to this gradient here. In other words, the areas that are red in our gradient are going to be moved out more than the areas that are blue, and that's based on the distance, right? So I'm going to preview off the attractor point preview, and we're just going to focus on geometry. So what I want to do is I have the amount of movement coming out of the trim tree. Now I want to find the direction. So to do that, I'm going to find the normal of a surface. Now, if you don't know what a normal is, essentially you can think of it as a vector that's perpendicular to a surface at a given point. So normal to surface, I will rely on Google to sort of show an image. I'm sure it has a good one here. So there is normal. So you can see that it is perpendicular to the surface at a given point. So we're going to find this for each of these points on our original lofted surface here. So to do this, we'll take our we're going to take our flipped data matrix, so our points organized in vertical columns. And what we're going to do is we are going to go to surface analysis and then surface closest point. We're going to take our flip matrix points output, plug into the point input of surface closest point, and we're going to take our loft and plug into the surface input. And essentially the reason why we're doing that is we're just getting the UV coordinates of these points. So we could grab the UVs from back here, but since we flipped the matrix, this is just kind of a nice way to regain those UV points. It's just kind of a straightforward linear method. So now what we're going to do is we're going to find these normals. So we're going to go to surface, analysis, evaluate surface. The surface will be our loft. The UV will be the UV points output. And now you can see there's an N output, which is the normal. If we want to visualize this, we can go to display, preview, display, vector, vector display. The anchors can be the point from the surface closest point. The vectors will be the normal. And now you can see all the little vectors. You can see they're perpendicular to the surface at the given point. So I'll just delete this vector display. We don't really need it. What we do want to do, though, is take our remapped values, which have been trimmed, so they're in the same data structure as our normals, and we want to adjust the amplitude of these vectors. So how long are they? So we are going to go to vector, vector, amplitude. We'll plug the normals into vector and the trim tree data, so these are the remapped values, into amplitude. So we can't see anything happening here, but what we're going to do now is we're going to go to transform, Euclidean, move. And what we'll do is we'll take our flipped points, so our flipped data matrix there, plug into geometry, and we'll take the resulting vector from the vector amplitude output and plug in T, so the translation vector. And now what we can see is we have a crazy offset, or at least I have a crazy offset. And the reason why I do that is, or have that, is because it looks like my domain is too long. So this is why it's nice to have a slider. So you can see that what's happening here is that these points are being offset based on these attractor points. So if I move these attractor points around, you can see that the points are kind of shifting depending on their newfound distance from said point. So once we've done this, maybe we can group all of these components here. And we can call this group offsetting points based on attractor points. And we can preview off all of this stuff here except for the offset points. So now what we're going to do is we're just going to draw curves between these. So we're going to go to curve, spline, interpolate. So curve, spline, interpolate. Take our moved points from our move component, plug into V. And now you can see this is giving us these kind of wild wavy curves. Now these are pretty intense. What I might want to do is just change my domain end to something smaller, maybe 10. Maybe that's too small. Find a happy medium. 50. Sure, this looks good for right now. Of course, if I want to change the direction, maybe I want to offset on this side instead of this side, I could always maybe even go -50 to 0 and offset on this side. So that's always an option too, sort of play around with the sliders, see what happens. So we have our curves here. Maybe I'll preview off these points. So we have our offset curves. And then we have our original curves here. So what I'm going to do is I'm again going to go to curve, spline, interpolate. Take my flip matrix points, plug into the interpolate curve. So we can consider these the backs of fins. I'll preview off my flip matrix points there. And then what I'll do is I have my, essentially you can think of it as the picket base, or the back of the picket. I have my wavy front of the picket. And what I'm going to do is I'm going to find the endpoints of these curves and connect them to create surfaces. So I'll go to curve analysis endpoints. I'll grab that twice. Curve analysis endpoints. I'll plug that into both of these interpolate curves. So now you can see I have the endpoints for my wavy front of pickets, the end of curves for my straight back of pickets. And what I'll do is I'll go curve, primitive line. I'll connect the start points. That's going to give me this bottom line right here. And again, I'll go curve, primitive line. This will give me, I'll connect the endpoints. So the endpoints of my front of curve, endpoints of my back of curve. This will give me curves at the other end. And then I'm going to go to curve, utilities, join curves. And I will join my interpolated curves. So this curve at the back of my pickets, I'll plug into the curve join. My offset curves, I'll hold shift so I see the little green arrow and the plus icon. I'll plug into the curve input as well. And then my two lines connecting the ends of these two curves, I'll hold shift and plug them both in as well. I'll preview off all of this stuff except for my join curve. And then at this point, what I'll do is I'll flatten the output. So now you can see in this list, I have a bunch of closed planar curves. So that's what you want to see. And they're corresponding to these pickets right here. So I will now just simply go to surface, freeform, boundary surfaces, plug my closed curves into my boundary surface. You can see this is giving me those wavy pickets, like so. If I want to increase the points in horizontal, so the densities of these pickets, I can do that. If I want to increase the offset to something wild, I can do that. You can see, however, if I do this, there will start to be intersections. So you're going to need to adjust your surface accordingly so you don't get any intersections. Maybe I'll stretch this out to avoid some of those intersections. And of course, as we move our points around, we will get different patterns on our surface. So the closer the point is to the surface, the more that area will be offset. Now, to give these some thickness, what we'll do is we will take our trim surfaces, our boundary surface output here. We'll go to Analysis, Evaluate Surface, plug our boundary surfaces into there. And what we're going to do is we're just going to figure out the normal of these surfaces. So again, the normal is the vector that's perpendicular. So for instance, this surface here, its normal would go roughly in that direction there. We're going to find it at the middle of these surfaces. It doesn't really matter where we find them because you know, they're flat. But roughly the middle, we can right-click UV, go to Set One Point. Make sure the type is now coordinate, because we're going to type 0.5, comma 0.5. Hit Enter. And the other thing we want to do is we want to right-click on the surface input and go Reparameterize. And that will give us roughly the center of all of these surfaces. It'll also give us the normal. So what we're going to do now is we're going to go to Surface, Freeform, Extrude. Extrude has two inputs, so Profile, Curve, or Surface. We'll plug our boundary surfaces into the B input. The extrusion direction will be the normal here, so we'll plug that into D. But before we do that, actually, sorry, we want to control the thickness of our extrusion. So what we'll do is we'll go Vector, Vector, Amplitude. We'll take the normal vector, we'll plug into V. The amplitude, which is the length value, so the length of the extrusion, we'll create a slider for it. I'll create a slider going from 1 less than maybe 5. If we want to use floating point numbers, maybe instead I'll go 0.1 less than 5.0. So 0.1 less than 5.0. I'll plug that into the amplitude. And now the extrusion, I'll plug the vector amplitude into the extrusion. And you can see as I move this slider, it's going to change the thickness of the extrusion. So once you're happy with your shape, of course, you can adjust in Grasshopper. You can bake it, but before we do that, why don't we just preview off the boundary surface, the evaluate surface, group all of this, these final components here, right-click this group, and we will label it extruding the fins. So now we can bake this extrusion. You know, at this point, it's probably a good time to save your Grasshopper file. So, you know, I'll just save it as fins. You can save it as whatever you want. And we can see if we switch to rendered view, we kind of have this waving surface similar to this precedent we saw here. So if you want to do something like this precedent, you know, it actually wouldn't be too hard. You might just need to break this up into several different surfaces. So for example, what you could do is you could draw, you know, a few lines like this. It looks like there's filled corners. Oh. So this could have filled corners. You could go surface, extrude curve straight. And then in Grasshopper, you could try just referencing a surface. Maybe instead, actually, just so we keep this consistent, instead of lofting there, I can just have these two curves. So input curves, I'll right click, go to set multiple curves, 1, 2, and now you can see that this picket kind of scheme works very similar. So of course we'd want new attractor points. So here are my new attractor points. Set multiple points. And of course you would want to change the density. So points in horizontal, maybe you could change that slider there and change it to, let's say, 200. Let's switch this to 200. And there's something that looks more convincing. It also looks like we probably want to change the offset more. So, you know, change your offset so it's a little bit more dramatic. Whoa, maybe not that dramatic. Let's switch to -500. So there. So this could be, you know, an interesting output of your the parametric facade for your assignment 3. So this is the first thing I want to do. So this is sort of, not only is this showing you a very particular language that's kind of interesting, but more so I want you to think of the attractor point is the first sort of parameter we're dealing with. So this language is an output, but the parameter, the attractor point, is input 1. So what we're going to do is we're going to do this same language using a different input. The input is going to be a image sampling, just so you have a little bit more control over your distance. And then we're going to move from, we're going to keep the parameter set as image sampling, and we're going to move to a new language. So we're sort of shifting through parameters and techniques right now. So parameters and outputs. So this ends sort of part 1 of this video, but up next I'll be doing something similar, but with image sampling. Thanks. Hey there. So what we're going to do in this video is we are going to create the same kind of waving facade. We're going to do it horizontally instead of vertically, but we're going to use image sampling to do so versus the point attractor method that we had done before. So I'm going to do some things that will be direct review of what we just did. You can use components, definitions that you've already set up, but I'm just doing this to sort of start from scratch. So what I've done is I've drawn one curve here. It's just a few straight segments with some filled corners. And I'm going to select this curve. I'm going to hold Alt, and with the gumball, I'm just going to drag it up. In Grasshopper, I'm going to go to Params, Geometry, Curve. I'm going to right-click this parameter and go Set Multiple Curves. I'm going to select these curves from the base and move up. I'll right-click this parameter and call it Input. I'll call it Wall Curves. Now, I'll go a little bit faster for a few of the beginning steps here. Refer back to the first part of the video if you want a more thorough explanation of the lofting, etc. So from these curves, I'll go to Surface, Freeform, Loft. We have our lofted surface. And then from there, I'm going to go to Surface, Utilities, Divide Surface. I'll take my loft, plug into the surface, and this will give us our UV points. Now, one thing to mention, as we'd mentioned before, is, we mentioned earlier in this class, that every surface has an internalized coordinate system. So if we want to get a sense of that internalized coordinate system, what we can do is we can go to Params, Input Panel, and in the surface divide output, we can plug our UV output into the panel. And what this is telling us is, you can see our first point here is 0, 0, 0. This more or less tells us that this corner down here is considered 0, 0, 0. So that's how Rhino and Grasshopper consider this surface we've just created. On this corner, so I scroll all the way to the bottom, you can see that Grasshopper and Rhino consider this upper right-hand corner to be 1195, 3153. So in other words, our coordinates are going from 0 to 1195 in this direction and 0 to 3153 in this direction. So the U in the V direction, or vice versa. This could be V, this could be U. So what we want to do though is we want to set both the U direction and the V direction to be 0 to 1. So in other words, instead of this 1195, we want it to be 1 1. So 0 to 1, 0 to 1. And the reason why we want to do that is we're going to use the image sampler, which samples an image that we reference from 0 to 1, 0 to 1. So to reparameterize the surface, to reset its internalized coordinate system from 0 to 3000 or whatever, all we have to do is right-click the surface input of S-divide, so surface divide, and go reparameterize. And now you can see our internal coordinate system goes from 0, 0 in this corner, presumptively, to 1, 1 in this corner. This third number here is the W value, and it doesn't really have any effect for a two-dimensional surface. It has no depth, so we don't have to worry about W. It's always going to be 0. So since we have the UV points, essentially what we're going to do is we are going to now sample an image. So to do so, let's go to params, input image sampler, and we'll take our UV points and plug them into the image sampler. So your definition should look like this. Now, what I might want to do, and I sort of forgot to do after explaining UV, is play around with the resolution of both U and V. So increase the amount of U segments, increase the amount of V segments. So to change that, I'll just double click on the canvas and I'll create a slider. So I'll go 2 less than 500, hit enter, and I will go Control C, Control V to copy that slider. I'll plug the first slider into the U, second slider into the V, and as I move my first slider around, I see it U corresponds to the vertical direction. So I'll right click my U count slider and call it U vertical direction. V count, as I move this slider around, it controls the horizontal count. So I'll call it V horizontal direction. And I'll move these sliders to the left there. Now, what I'm going to do is I have this image sampler, my UV output's plugging into it. I'll double click the image sampler. And what image sampler does is it samples an image based on a 0 to 1 domain by default. And that's why we've reparameterized our surface, so it would be correspondingly 0 to 1 and 0 to 1. So when you open the image sampler, there's the X domain, 0 to 1 by default, Y domain, 0 to 1 default, and we're gonna change, or we're gonna leave these X domain and Y domain to be 0 to 1. So we'll go with default. Likewise, tiling, we'll just leave it as tile as default. And for channel, we are gonna switch it to color brightness. So we're gonna work with grayscale images, so just make sure that black and white, the color brightness is selected. From here, you're going to select a file, so a file you want to sample. Now, in the Dropbox in today's class, there is an image, so this wave pattern here, feel free to use that. I will switch to this, but I'm going to switch to another image just to demonstrate something that happens when we're image sampling, but this wave pattern is there. I'm going to choose this pug face, and I have a pug. I have two actually, so they're cute. So I'm going to sample a pug. What you can see is happening is this image here has different brightnesses across both its X direction and its Y direction. So what the image sampler is going to do is it's going to move along what it thinks is the U direction, so U equals 0 to U equals 1. And it's going to say this point here is dark, so it has a brightness value of 0. So it's going to return a value of 0. Whereas this value, let's say at approximately 0.5 in the U direction and 0 in the V direction, it's going to return a value of closer to 1. So it's very bright, so it's closer to white. So that's how this works. Let's click OK, whatever file you have. You can see it's converted it to a grayscale image. And to see how this is actually registering with our actual points on our surface, let's sort of do a custom preview. So to do that, I'm going to go to params, input, gradient. Now our gradient by default is sort of this heat map color scheme. I'm going to right click it and go to presets and click on the black and white grayscale gradient. And if we look at our L0, L0 is corresponds to white, so it goes 0 to 1 equals black, whereas our image sampler does the inverse. So white is 1, black is 0. So what we can do is we can just take our nodes on our gradient and invert them. So now 0 corresponds with black, white corresponds with 1. We can take our image sampler, take the output, plug it into T. That is the parameter along the gradient range. And now what we can do is we can go to display, preview, custom preview. The geometry that we're going to custom preview are our points, so not our UV coordinates. So these are coordinates. They aren't actual points, but our points output, so the P output of surface divide will plug into geometry, and the material will come out of our gradient here. So let's plug it here. So let's preview off everything else and see what we get. So if we increase the resolution, you can see that we get this cute little pug in our points. However, you'll also probably notice that this pug is sideways. So why is that happening? Well, if we think about our U direction for our surface, it's our vertical direction. But if we double click on the image sampler, it's going to count always U in the horizontal, V in the vertical. So the reason why our U is in the vertical direction is because we lofted going from a bottom curve up, right? So U is always the direction of the loft. So there's some things we could do. You know, we could always loft in the this direction. So, you know, if we loft from left to right, then our image will be sampled left to right. But in this case, where, you know, we're building a wall and you usually build from the bottom up, we want our image to correspond. So you could flip the matrix and play around with your UV points. But to be quite honest, I find the easiest thing to do is just to be aware of this issue. And then in Photoshop, here's another image I was going to sample. You can just take your image, so in this case the pug, and then you can rotate it. So image rotation, 90 degrees clockwise, save the image. Rhino should automatically update. So you can see now in image sampler, the image is rotated, but in our actual point sampling itself, you can see that the dog here is the proper way. So that's how I sort of get over that issue. Now you can still see that the face is stretched out a bit horizontally, but you know, that's because of the geometry of the surface. So maybe you could distort your image in Photoshop. Maybe it's ironic that a brachycephalic dog has a stretched out muzzle, but you know, in this case, that's what's happening here. I know that it's cruel to breed pugs for smushed faces, so we adopt. But anyways, I'm going to switch to this wave pattern. So what I'm going to do is I'm going to double click this little image sampler again. I'll change the file path. I'll click the three little dots and I'll switch to the wave pattern. I'll click open, click OK. Now this wave pattern is less apparent because it's more abstract than a dog face, but there is a certain, I'll call it horizontal dynamism. Oh, it's late. Dynamism to this image. So I want to retain that in my final facade. So what I'll do is likewise in Photoshop, I'll go to open, I'll find my wave pattern, and you'll want to do this too. And I will just go image rotation 90 degrees clockwise, and then I'll save it. If for some reason it says you can't save it, then just do save as. So wave pattern rotated. Click OK. And now I'll double click on this and choose the wave pattern rotated. So that's more what I want. Okay. So now that we've done that, I'm just going to take the gradient in the preview component and I'm going to preview off. I'll group this and I'll just call this image sampler sample confirmation. I'll preview back on my surface divide. And what I'll do is, since my point density is so high here, I'm just going to reduce it to something more reasonable. So the U vertical direction I'll reduce to 30. The V horizontal direction I'll reduce to 40, let's say. Now, simply what we can do here is we can offset these points similar to what we did in the first example in this video. And I'm going to work with horizontal bands of points this time instead of vertical ones. So I won't use flip matrix. If you do want to use if you do want to set up vertical bands, you would just flip the matrix like we did in the last video before the image sampler. So just refer to the first part of the video if you want to do that. But simply what I'm going to do is I'm going to remap the values coming out of the image sampler from 0 to 1, which they are coming out of the image sampler, to something of my choosing. So to do that, I'm going to go to Math, Domain, Remap Numbers. So remap numbers, it remaps numbers into a new numeric domain. The value input will be coming out of the image sampler, so image sampler goes to the V input. The source domain is 0 to 1 by default, which is great. That's what the image sampler outputs. And the target domain will create this. So this will be our offset. So we'll go Math, Domain, Construct Domain. And this will grab two sliders. So I'll just double click on the canvas. And likewise, I'll go -500 to 500. Or -500 less than 500. Enter. And I will copy and paste that slider and put it into the A input, the B input. And I will just set this as 0 to, let's say, 100 to start with. And now you can see we have our remap numbers. Now, in surface divide, we also have the normal vectors. So the normal vector, is a quick refresher, is the vector which is perpendicular in both the U and V direction of the surface at any given point. So in this case, this bottom point here, it's going to come out roughly that way. So what we're going to do is we're going to take these remapped values and use them as the amplitude, so the lengths of the normal vectors coming out here. So what we'll do is we'll go to vector, vector, amplitude. The normal vectors will be the vector. The amplitude will be our remapped values. And then finally what we're going to do is we're going to move these surface divide points. So we'll go transform, Euclidean move. The geometry we want to move are the surface divide points. So P output of surface divide goes into G input. And the vector amplitude output, V, so the amplituded normal vectors will go into T. And then what you can see from there is that we have this kind of wavy points system happening. So what we will do now is we will go to curve, spline, interpolate. We'll take these moved points. We'll plug into the V input of interpolate curve. And now if we preview off all our points, you can see that we get these kind of interesting wavy curves. If we really wanted to, what we can do is we can go to Surface, Freeform, Loft. We can plug our resulting curves into the C input of Loft. We can right-click the C input and go Flatten, so all of these curves are in the same branch or list. And it will actually create kind of an interesting twisty surface. So, you know, if you prefer having a facade that looks something like this, you know, this is always perhaps an interesting way to create a, it'd probably be a cast element, but an interesting surface for your lookout tower. So that's one option. The other option, though, if I just delete that, is to create the horizontal louvers or fins like this Preston image right here. So what I can do for that is I can take my original subdivided curves. I'll also put them into a curve, spline, interpolate component. So points output goes into the curve input. So now we have these sets of curves. So the back of the fin, the front of the fin. And then from here, we'll go to curve analysis endpoints. We'll do that twice, curve analysis endpoints. So the front of the fins, our first interpolate curve, will plug into a curve endpoints. The back of the fin, so our second interpolate curve, will plug into the endpoints. And then we'll connect these endpoints with a line. So we'll go to curve primitive line. We'll do that twice, so curve primitive line. We'll go start point to start point, so you can see that's drawing these lines right here. Now, maybe we don't want to go down to 0 distance right there. If that's the case, all we have to do is go back to our domain start and end and change our domain start to maybe, let's say, 5. So now we have small ends, so that's no problem. And then we'll connect our endpoint to endpoint. So you can see that's the other side there. Once we've done that, we can simply go to curve, utilities, join curves. And holding shift, we can plug all of these lines into the join curves component, preview off all of this. And now we have our curves. So we can flatten the output of this, and we have a bunch of closed planar curves. Now from here, we simply have to go to surface, freeform, boundary surfaces. So now we have our surfaces. I can preview off our join curves. And since we know that these curves are, or these surfaces are wanting to be extruded straight up and down, we don't have to worry about finding the surface normal to the center point of these surfaces. We can simply grab a vertical vector. So we'll go to vector, vector, unit Z. We can create a slider that goes into this vector that will define the thickness of these fins. So I'll double click on the canvas, set a floating point value by going 0. Let's say 1 less than, let's go 50.0, hit enter. I'll set it to 10. I'll plug that into the factor input of the Z, or the unit Z vector, so that's straight up and down. And then I'll go to surface, freeform, extrude. I'll plug the boundary surfaces into the B input, so the profile curve or surface to extrude. and the extrusion direction will be the Z vector that we've defined here. So now you can see that gives it some thickness, and if we want to increase that thickness, we can just increase the vector there. So once you're happy with that, we can just bake that extrusion. Group, sure. And that can be your kind of, maybe that's how you do your facade. So that's kind of an interesting way to come up with a facade like that. So it's quite striated, so that could be an interesting aesthetic which you go for. What I'll do is I'll zoom into the grasshopper definition right now, so you can pause the video, and this ends section 2 of this class. So if you have any questions, email me, and I hope this works out for you. Thanks. All right, so the third sort of surface I want to look at today is this kind of parametric surface. You see there's essentially a whole bunch of oculuses that have different openings. Now this might be based on a view, this might be based on solar analysis, but what we're going to do is we're going to create a flexible system that allows us to achieve this gradiated opening kind of pattern. Now, we're going to do this based on image sampling, but you, of course, could do this based on some sort of solar analysis, which we'll touch on next class, as well as a view analysis, since this is a lookout tower. Furthermore, in this example, I'm going to be working with very simple rectilinear geometry. However, I would encourage you to try different sort of curve inputs, and I'll sort of let you know what I mean by that when we get to that part of the definition. So I'm going to start out with a curve. I've just drawn a 2D curve in Rhino. And like all of these examples, I'm just going to select it, hold Alt, and drag it up. So I have two curves there. In Grasshopper, sort of bringing up my Grasshopper window, I'm going to reference both of these curves. So I'm going to go Params, Geometry, Curve. I'm going to set multiple curves. Again, I'll start from the bottom, work my way up, and I'll call these input curves. Like the other two examples, I'm going to loft these. So I'm going to go to Surface, Freeform, Loft. And now we just have our lofted surface. So what we're going to do here is we're going to use box morphing. So I think we touched on this in Module 1, depending on who taught your Module 1. This might seem like a distant memory, or it might seem totally new to you. So we'll cover this again. So essentially what box morphing is arraying a bunch of boxes on this surface and then taking geometry like we did in the column class, morphing it from a reference box onto the surface in this case, rather than a large column morphed to a spot underneath the bridge. So to do that, we first need to subdivide the surface, and we'll do it a little bit differently than the last two examples. What we're going to do is we're going to subdivide the domain in the U direction and the domain in the V direction. Now, since we're going to be working with the image sampler again, what we want to do to this surface before we subdivide it is reparameterize it. So set its domain from 0 to 1 and 0 to 1 in the other direction. So if I hover over the output of loft, and I right click it, you can see there's no option to reparameterize it. So if you ever want to reparameterize the loft, what you can always do is you can go to Params, Geometry, Surface, plug your loft into the surface, and then on this surface parameter, right click the surface parameter and go reparameterize. And that's just going to make sure that our U's go from 0 to 1 and our V goes from 0 to 1, which we need for the image sampling that we're going to do further on in this definition. So we're just thinking ahead here. It might be good habit to do this whenever you're lofting curves. Who knows? But anyways, what we're going to do is we're going to subdivide the U and V domain of this surface now. So to do that, we can go to Maths, Domain, Divide Domain Squared. And we can plug this surface directly into the base domain input, so input I. And you can see here, it allows us to choose the number of segments in the U direction, number of segments in the V direction. So we'll create 2 sliders for both of these. I'll double click on the canvas. I'll go from, let's say, 3 less than, I'll say 100, click enter. I'll copy this, Control C, Control V, plug the first slider into U, the second slider into V. Now, to see which direction is which, what I'm going to do is I'm going to create these surface boxes. So I'll go to Transform, Morph, and then Surface Box. So hover over this, create a twisted box on the surface patch. It has 3 inputs. So the base surface will be our reparameterized surface coming out of the loft. Our surface domain will be our segments coming out of our divide domain squared. And then our height will be another slider. But before we deal with height, let's look at the U count and V count and the effect it has on a surface box. So you can see it's very low resolution right now because we only have 3 segments in each direction. But if I increase the U count, you can see that U is corresponding to the vertical. And again, that's because we lofted upwards from our bottom curve. So I'll right click my U slider and just call it U hyphen vertical direction. And my V count, I know it's the horizontal, so I'll call it V hyphen horizontal direction. So now you can see that we can increase both of these. It increases the resolution. The final thing that we want to do is we want to change the height of the surface box. So you can see right now these are 3-dimensional surfaces, but they are extremely shallow. So what we're going to do is we're going to create a slider, double click on the canvas, and I'll go -500, less than 500, hit enter, and I'll put that into the height. So again, I choose the -500 to 500 because it allows me to choose which side I want my surface boxes to be extruded onto. So now that we have essentially created these surface boxes, what I want to do is, again, I mentioned we're going to do an image sampler, and we're going to do that in order to get this gradiated oculus opening pattern. So what we're going to do is we're going to find the center point of all these boxes. We're going to put those into the image sampler. And then from an image we're going to sample, that will determine how big our openings will be. So let's do the image sampling now. To get a point that we'll sample, essentially what we're going to do is find the center point of the box. So we'll go to Surface, Analysis, Box Properties. Take our surface box, plug it into the box input, and you can see in the outputs, the first one is center point of box. So that's what we're going to use. Now, remember, we need to refer these points back to a UV value between 0 and 1 in order to use the image sampler. So what we'll do is we'll go to Surface, Analysis, Surface Closest Point. So find the closest point on a surface. The first input's the sample point. That'll be the centers of our box properties. And the surface will be the reparameterized surface coming out of our loft. And that's why we reparameterize, because we want all these surface closest points, you can see that one right there, having a value between 0 and 1 to put into our image sampler. So perhaps what we can do at this point, now that we have our surface closest points, is we can group all of this. Seems like a decent place to group it. And we can call this surface boxes and UV points for sampling. So I'll make my grasshopper window a bit bigger. So now what we're going to do is we're going to image sample. So I'll go to params, input, image sampler. again, we can plug in our UV points. So not our points, but our UV points, the coordinates. Plug UVP into our image sampler. I'll double click the image sampler. So X domain by default 0 to 1. That's why we reparameterize. We know 0 to 1 in the vertical is U. Y is 0 to 1. That will count as our V, which is in 0 to 1 in the horizontal. We are going to sample the color brightness again. Feel free to play around with the RGBA values, red, green, blue, alpha, etc., etc. I usually do brightness. And we are going to update our file path. So I'll click the 3 dots. In today's class folder, there's a dot pattern here. You can, of course, choose your own. And I'll just click OK. So now we're sampling between 0 to 1. That corresponds to the vertical value. So again, if this image or your sampled image needs to be rotated, just do that in Photoshop. The V, which is the horizontal value here, as we can see, we've labeled our V slider horizontal. It corresponds to the vertical in this image. And what's going to happen is a UV of 0.5, 0.5, for instance, on this surface. We'll sample 0.5, 0.5. And since that is pretty much pure black, it's going to return a value of 0. So 0 equals black, 1 equals white. What we'll do is, now we've sampled this, is this sampling is going to be used to adjust the opening of an oculus, as we can see around here. So now we need to make these openings. I'm going to make a very simple one in Rhino, but I would, encourage you to make a very kind of unique one. Maybe I'll do a fancy one at the end to look at what it looks like, but I'll start out with something quite simple. So I'll click the rectangle tool here. You can also just type rectangle, and I'll just drag out a rectangle like so. I'm holding shift to make sure it's a square. And then I'm going to reference this rectangle in Grasshopper. So I'll select it. I'll go to params, geometry, curve. I'll right click this parameter input. I'll rename it to, let's call it Oculus outer shape. You'll see why it's outer in a second. And then we'll go set one curve. So it's referenced because it turns green. Now, what we want to do is we want to essentially offset it. So the offset's going to be the inner opening of all these window panes, oculus, what have you. So we are going to go to curve, utilities, and then we're going to go to offset curve. So that's curve, utilities, offset curve. The curve we're going to offset is our oculus outer shape. The distance is going to be based on our image sampler here. The plane can be left as default XY because I drew it on the XY plane here. And the corner type, I've left it as sharp. You can play around with switching this to, round, smooth, chamfer, whatever you want. One thing to note, though, is distance equals 1 is offsetting outwards, whereas we want to offset inwards. So just keep that in mind for now. We'll address it, but it's just worth noting which direction your curve is offsetting by default. So we have a bunch of values from 0 to 1 here. We want to remap them to something that makes sense. So what we'll do is we will go to maths, domain, and then remap numbers. The values from our image sampler will plug into the values input of remap numbers. The source domain is 0 to 1 by default, which is great because the image sampler has a domain of 0 to 1 by default. And the target domain will kind of play around with this. So what I mean by that is we'll take a slider. I'll double click on the canvas and I'll just type, let's say 10 less than, I'll type 1000. Not sure if that's what I need. And what I'm going to do is I'm just going to take this slider and plug it into my distance. You can see again, it's offsetting in the wrong direction. So what I'll do is I'll right click on my distance input. I'll go expression. I'll type -x. So now it's offsetting on the inside. And what I'm doing here is I'm just figuring out what my max offset should be. So it looks like my max offset for this shape is 664. I'll say 660. But yours might be different. So what I'm going to do is I'm going to take this distance slider, plug into my target domain in my remap number. So now you can see if you just plug in one value, it's going 0 to 664. And then I'll take this result and plug into the distance component or input of my offset component. And now you can see what happens is I get one offset for each sample here. So that's why we get kind of this interesting you know, offset pattern here. So you can see that all these offsets are in their own list. We have leading zeros here, so 0, 0, 0, 0, 0, 1. If you want to get rid of leading zeros just for organizational reasons, you can right click and go simplify. And now you can see we just have all these curves, single list, 0 to 186. So what we're going to do now is we're going to loft between this outer curve and these inner curves. First thing we want to do though before we loft is we want to give our loft some thickness. So we'll move up our offset curve. So I'll go transform, Euclidean move. I'll plug the offset curves into the geometry input of move. And my translation vector, it actually doesn't matter because what's going to happen is these offsets and the lofts are going to be scaled by the height of these boxes. So it actually doesn't matter if it's only moved up a tiny bit and we can't really see. So we won't worry about putting anything in here. The translation vector of 0, 0, 10, aka 10 units straight up, works fine enough for us here. So what we're going to do now is we're going to simply loft. Now, it's not quite so easy because we have 186 offsets or 187 offsets, each in their own individual list, and we have only one original curve. So what we're going to do is we're going to repeat this curve as many times as we've sampled, and then we'll loft. So what we're going to do is we're going to go to Sets, Sequence, Repeat Data. The data we're going to repeat is our oculus outer shape. I'll plug that into data. And the length of the final pattern will be the length of this list. So to find that out, what we'll do is we'll go to list, list length. I'll take the remap number output. I'll plug into list length. You can see it tells us how many numbers we have, or number of items we have. So 187, I'll plug that into list length. And now we have this one outer shape repeated 187 times in my case. Because each of these offsets and moved up curves are in their own list, you can see we have 0 to 186 branches. What we want to do is we want to graft the output of this repeat. So right click the output graft. You can see we have all these leading zeros, whereas this move component has no leading zeros. So we'll right click the output of repeat, go simplify. So now you can see we have 0 to 186 for our lists. Here we have 0 to 186. The data matches, perfecto. So what we can do is we can just go to surface, freeform, loft, and we can plug in both these components. So the move component, I'll hold shift to see the little green arrow and plus icon, plug into loft as well. And now you can see we have all these different lofts right here. So since that's done, what we can do is we can select all of these components, right click outside them, group, and I'll right click and I'll name this group lofting openings for each sample point / each surface box. And I can preview off everything except for these lofts. So like I said, it doesn't matter that they're quite flat right now, because we'll see that when they're morphed into these boxes, they'll get some depth, or rather some height. So what we can do now is let's preview off our surface closest point, our box properties here, to just see our boxes. We're going to do a box morph now. So what we can do is first we can create a bounding box around these lofts. So we can go surface, primitive, bounding box. We'll plug our lofts into the bounding box. And from here you can see that by default it is per object, so we have 187 boxes here. What we're going to do is we're going to right click the geometry input, click flatten, and then still we have 187 boxes because the setting is set to per object. So I'm going to right click the bounding box component, go to union box. Now we have one box surrounding all of these lofts, which is what we want. And now what we'll do is we'll do box morph. So we'll go to transform, morph, box morph. We will look at the inputs. So the first input is the base geometry. That is going to be our lofts. So our lofts still grafted. We know they're grafted because they have this dashed line here. We'll go into G, so geometry. The reference box will be the union box. So I'll plug the union box into reference. And the target box will be our surface boxes here. Now, these surface boxes, you can see that they're in one list. There's a solid line here. So what we need to do is we need to right click on the target box input, and we can click graft. Furthermore, because there's no leading zeros leading into our G input here, so 0 to 186, just as a precautionary step, I'm going to right click the input to T, go simplify. Simplify never really hurts. And I'm going to take the surface box component here, and I will plug it into the morph component there. And now you can see what happens is we have our differing oculuses based on this image sampling here. So you can see that it looks like it's sampled this way, but we have one dot corresponding to that, one dot corresponding to the center, this dot there, so on and so forth. So you might use a different pattern, as well as you might increase the density to get a pattern that's a little bit more interesting. So I'll increase this in both directions as my computer cries. So that's kind of interesting. What I'll do now is I will preview off all these lofts, and what I'll do is I'll take this box morph, I'll right click, I'll bake it, and I'll go group, yes please. I'll close my grasshopper window and just look at this in rendered view. So it looks kind of interesting, right? From the side, you can't really tell the difference. From the front, you can. So that's essentially how you do geometry like this. As I mentioned, you don't just have to use a rectangle. So I'll delete that. And how about instead of a that rectangle, we can try, let's say, a star. So to make a star, I will go to the little star tool here. I'll go like that. And instead of this rectangle, I'll delete you rectangle. I will select the star. I'll disable these components for a second just because I want to see what kind of offset I should be working with. So I'll right click, set one curve. I'll take a look at the offsets that are happening right here. Preview on to see. So it looks like, as you can see, this is offsetting too far. So I'll decrease this offset maybe to like 200. Still looks like too far. So maybe I'll decrease it to 150. that looks about right. And then now I will enable all the other components. So I'm not really sure what this will look like, but it should be interesting. So a lot of times in Grasshopper, it's kind of fun to just play around like this. So there we go. We have our stars. Now, I'm not quite sure if this I'd consider this successful. Maybe I'm going to decrease this. Maybe I'll decrease this. So yeah, I'd say overall this looks pretty bad. But you can play around with different patterns. One thing I will say, just sort of while I'm thinking of this, is if you are going to make your own custom pattern, it's worth thinking of how it sits in relation to a box and to make it tileable. So what I mean by that is rather than dealing with this kind of dumb star, is maybe it's better to draw out your pattern. So I'm just drawing a pattern. Oh, Control C, Control V. And what I'm doing is I'm just making sure that it is tileable. So what I mean by that is I drew this curve, I'm mirroring it around these axes. I am going to use the curve Boolean tool to make this kind of interesting curve like so. And then I'm going to set this tileable curve. So again, play around with making your own tileable curve on Wednesday if you have any questions on how to do this. And now you can see that this curve, I'd say, is looking a little bit better. That being said, the offset is probably not enough, so let's switch this offset to 300. Maybe even go a little bit further, 340. And now you can see that what we're working with here, it does look a little bit better. So in this case, it's kind of strange because it's almost like the openings, you can see, are more prominent in this case than the actual oculuses, which are in the side. So maybe in that case, you know, if I were to maybe redo this, so right now I'm just kind of jamming, I guess. Maybe what I'd do in that case to make these openings smaller, since they look a little bit too visually dominant to me, is I'd just take these points here and I would stretch them out. And you can see that Grasshopper's updating while I do this. So now those sides are getting a little bit less prevalent. Maybe I want to take these points here, also stretch them out. And now you can see I'm sort of creating a different pattern. And again, maybe I want to adjust the offsets, all these things, all this to say that you can fiddle around with this stuff for hours until you find something that you like and works. So anyways, so there's another pattern. Once I'm happy with it, I will bake it, click OK. And there is my pattern like that. So we can see that it's kind of interesting. So play around with lots of different patterns. I think that these are starting to look kind of successful here. They maybe look less successful in the larger portions here. So play around with different patterns, different image sampling images as well, and hopefully you come up with something you like. Maybe this is the way that you create the facade for your tower. Now what I'll do is I'll end this section of the video just zoomed in on this definition like this, just so you can pause the video and rebuild it if need be. Okay, thank you.